All right, well, it's the top of the hour. I wanted to welcome everybody, depending on where you are, morning, evening, afternoon. Thank you for joining today's Wind Energy Science Leadership Series webinar. Today, we're going to be examining the increasing size of onshore wind turbine rotors. My name is Alex, and I'll be your facilitator for today's webinar, and that is a part of an ongoing series of educational webinars that include presentations and discussions on wind energy related topics, featuring speakers from the National Renewable Energy Laboratory, academia, and even industry partners. These webinars will discuss the challenges facing wind energy and the pathways forward to making wind one of the most prevalent energy sources of the future. Today, we begin with a panel of wind energy science and technology leaders to discuss new innovative technologies that maximize the advantages of large-scale rotors and their potential for increased energy generation. This work is part of the Department of Energy's Big Adaptive Rotor project that aims to create the next generation of land-based wind turbines with 206-meter rotors, which will increase capacity factors by 10% or more over a typical land-based turbine. This webinar will address the challenges associated with increasing rotor size for onshore wind turbines, which has contributed to substantial reductions in the cost of wind energy, and will discuss the feasibility of these large rotors and the design, modeling, and controls, advances needed to enable these technologies to further drive down wind energy costs. And before we begin, I have a few housekeeping items to cover. First, today's webinar will be recorded and available on demand on the website. Please mute your lines and turn off your cameras if you're not speaking. And next, we will encourage you to use the chat feature to ask questions, and we will be answering those questions at the end of the session. If we do not get to your question during today's webinar, we will be sure to follow up with you individually afterward. And finally, I would like to ask Daniel Laird, the Center Director for the National Renewable Energy Laboratory, to say a few words before we begin. Daniel?
Yeah, thank you, Alex, and good morning or afternoon or evening, whatever it is. Thank you all for making the time to participate. And yeah, I'll keep it quick, but NREL's wind energy research is comprehensive, includes everything from atmospheric and computational science, nearly every facet of turbine and plant technology, manufacturing, systems engineering, grid integration, environmental impacts and mitigation, to education and workforce development. So we are committed to the improvement of wind energy's cost competitiveness, grid friendliness, and U.S. and global deployment as we continue wind's long journey from alternative energy to just energy. So today's topic looks at concepts, challenges, and opportunities related to very large rotors. I personally find it interesting that when I started in wind research 25 years ago, there was a lot of discussion about whether wind turbines had reached their optimal size, and perhaps larger turbines would be less cost effective. Well, over the last 25 years, the turbines and obviously rotors have continued with unabated growth, continuously achieving lower costs of energy. And Nick and team will show us that the trend is going to continue. So with that, the speakers for self-introductions. Thank you.
Okay, great. Thank you, Daniel. My name is Nick Johnson. I'm a senior researcher at NREL, and my focus is on enabling the design of very large wind turbine blades and rotors. I'm the NREL PI for the Big Adaptive Rotor project, which we'll be talking about more today.
Hi, everybody. My name is Pietro Bortolotti, and I'm a researcher in the group of systems engineering at NREL, and I will talk about the design process and the bar designs.
Hi, everyone. My name is Nickar Abbas. I'm a PhD student at CU Boulder working in conjunction with NREL, and I'll be talking about the control systems for this project.
Hi everyone, I'm Kelsey Shaler. I'm a researcher here at NREL, and I'm going to be talking about a tool we developed to overcome some of the aerodynamic challenges with these big rotors.
Okay, great. Thank you all. Thanks again to everybody for joining. So today we'll be talking a lot about the Big Adaptive Rotor project. So before we get into that, I'd just like to acknowledge the rest of the team, the Big Adaptive Rotor team, not only an effort from NREL, but also with our sister labs, Sandia National Labs, Lawrence Berkeley National Labs, and Oak Ridge National Labs. So the agenda for today is first, I will talk about the motivation for large blades. Then Pietro will discuss the design process and optimization for large blades. Nikar will talk about the wind turbine controls of large blades. And finally, Kelsey will talk about the improved aerodynamic models for large blades. So if you want to hear about large blades today, you are in the right place. So what is the Big Adaptive Rotor? So the purpose of this project is to identify technologies that increase turbine capacity factor and decrease specific power, thereby increasing the rotor size to drive down the levelized cost of energy. So we define here the capacity factor is the actual power generated divided by the rated power of the wind turbine. Here, obviously, the power of the machine is defined by 1/2 rho, which is the air density, times the swept area of the rotor, times the rated wind speed to the third power. And obviously, the area for a wind turbine rotor is pi r squared, where r is the radius or the wind turbine blade length. And here, for the specific power, one of the things that we're trying to decrease is the rated power over the swept area of the blade, or of the rotor. So if we start out with a wind turbine rotor, again, obviously our area is the area of the swept area of the circle. If we increase that area by increasing the blade length and the rotor area, it has the impact that if we keep the power constant, we can actually decrease the rated wind speed. This is because obviously we keep the density of the air stays the same, the power stays the same, and we are increasing the area. So we can actually achieve rated wind speed at lower wind speed. Obviously, if we make the rotor bigger, we're increasing the area. And finally, if we're increasing the area of the rotor, we see that the specific power decreases because that term is in the denominator for the specific power equation. So to give this project a little bit of historical context, I'll kind of take you through some trends since the year 2009 up to the year 2018. From a high level, we can say that the nameplate rating of the wind turbines have been growing, the rotor sizes have been growing, the things that Daniel kind of talked about as well. And we can see too that the specific power ratings have been decreasing. So if we start with the machine rating, the megawatt rating of the machine, we can kind of look at this top left graph here. So the solid line in black kind of shows the average of the installed megawatt rating of wind turbines in the US for onshore turbines. We can see that in the year 2009, we had a lot of the smaller turbine ratings denoted in these red bars, so less than 2 megawatt machines. We can see that over time, the share of these machines has decreased quite substantially. And in 2018, it represents a very small portion of the installed capacity. We can also see that these other machines, the ratings have increased over time with finally these darker kind of brown colors representing megawatt ratings over 3 megawatts. And we can see that these types of machines are gaining a larger share of the overall portion of installed wind turbines. We can see also if we look then at the hub height hasn't changed too much. And this has to do with some other factors with FAA regulations. But we can see too that the hub height kind of is slightly increasing over time. We can see then if we look at the rotor diameter, this chart in the lower left, that in 2019, the rotors were quite small, less than 100 meters, and this made up most of the share, if not all of the share of the turbines, and we can see that that share has gradually and almost totally decreased in 2018, and the larger rotors, larger than 120 meters, are now gaining quite a big share of the overall market in the US. And we can see, obviously, too, the trend of the average rotor diameter has increased steadily since 2009, with the average rotor diameter being installed in the US around 120 meters in 2018. We can also see here that the average specific power of the machines has been decreasing steadily during that same time frame, and that, yes, the market was dominated by very high specific power machines, over 300 watts per square meter in 2009. And again, this number has gradually dropped in that same time frame. So with the BAR project, what we're wanting to do is really push the limitations to see where the constraints are in the system and where some of these scalings might start to break down. So we picked a very aggressive and large machine by today's standards at 5 megawatts, and also picked a very large rotor diameter, so of 206 meters, whereas we were seeing this average of about 120 meters in 2018. And we picked a very aggressive specific power rating of 150 watts per square meter, which is lower than anything that's kind of being registered in 2018. So to look at this data in a little bit different of a way, we can see that the average rotor diameter has increased 40% since 2009, and that's this green line here. In fact, we saw in 2020 offerings of 5 megawatt machines with rotors up to 170 meters. And installed in 2019, some of the largest machines that we saw installed in the US were 3.6 megawatt machines with 136 meter rotors. So we can also see that the nameplate capacity has been increasing kind of on that same rate along with the rotor diameter. So that's this dashed black line. So we can see it kind of ended up around the same place in 2018. So it also increased 40% in that time, same time frame. And also we can see too, the specific power almost did the same exact thing. So that's this purple line. So the specific power has steadily been dropping to the point of 30% since 2009. Also, we can see this is the average LCOE. We've seen a almost 60% reduction in LCOE since 2009. So all of these things are kind of correlated, and so we can see that the LCOE has decreased along with an increasing blade length and a decreasing specific power. We can also say that controls and other technology advancements have made these things possible. But yeah, we can obviously see a pretty good correlation with the blade length, rotor diameter, and drop in LCOE. There are limitations, however. I guess you could potentially see this this trend continuing until LCOE reaches 0 cents, and you know, everybody's happy and there are rainbows everywhere. But there are limitations. There are reality, however. So this trend will not continue forever. One of the biggest impediments logistically are transportation costs. So at some point, the blades are no longer transportable via traditional methods. So we do have these constraints on the physical dimensions of the blade. So the max chord, we have a constraint of 4.75 meters. The max prebend and sweep can be a maximum of about 4 meters. The maximum root diameter is about 4.5 meters. And then the length of the monolithic blade, so a non-segmented blade, could be about 70 to 75 meters. And this corresponds with about a 5 megawatt machine. So these are kind of the constraints where we can continue to, you know, transport blades in a traditional manner, mostly via rail, which is one of the cheapest ways to transport blades. So after 5 megawatts, the transportation of blades becomes very expensive. So we can see here in this chart We're here at about this 5 megawatt rating right now. We're actually really starting to be in this area. And so after that, the cost of transporting the blades really blows up and has actually quite a big impact on the overall LCOE equation, which would then lead you away from going towards larger and larger blades. So within the BAR project, we're interested in how we can kind of continue to keep that scaling trend going. One obvious solution here is segmentation of blades. So segmentation, it's a valid solution to overcome transportation constraints, and it is being pursued by various OEMs at the moment. However, this also comes with a however, you know, nothing is for free. We see here, obviously, with the blade joint that you are adding additional mass. So blades become 10 to 15% heavier. You're increasing complexity, so you're also increasing the cost of the blade. The blade has unknown reliability impacts, or the joint has unknown reliability impacts, as these machines are designed and built to be operated for 20 to 25, sometimes even 30 years. We haven't quite seen yet what the impacts of including these segmented joints in blades can be. But you can assume that it will have some sort of operations and maintenance effect, which could include downtime of the machine and also include expensive blades, expensive cranes to do the maintenance on the blades. And it could also be said that the assembly on-site requires additional manpower, additional labor, and so this may also be non-trivial. So while this is a valid solution to overcome transportation, it does come with its own challenges. So within the BAR project, we wanted to look at maybe an alternative to segmented blades, where we could actually keep a monolithic blade, so with no segments. So we looked into this idea of transporting the blades still by rail, again, which is one of the cheapest transportation solutions right now. This was initially proposed by DNVGL, where the idea here is that we would have the blades be so flexible. Again, we're talking about 100-meter blades. These blades would be so flexible that they can actually maneuver the curvature on the rail car lines. So we looked into this, and we ended up with blades that were very, very flexible. So flexible, in fact, that they were no longer able to be in the upwind configuration because that would lead to a tower strike during operation. So we changed this to a downwind configuration. Additionally, these highly flexible blades have other system level benefits. So, you know, we have lower blade mass, so we're taking some weight and structure out of the blade, leads to a lower blade mass, lower cost of the blade, leads to lower loads on the blade. And we're also seeing industry is very interested in pushing these limitations already. So to kind of summarize what I've talked about so far, within the BAR project, again, our main purpose here is to reduce LCOE, increase the capacity factor on machines, which I talked about, reduce the specific power. And so really here, the project focuses on these highly flexible rail transportable 100-meter blades in a downwind configuration. And we also use distributed aerodynamic controls to manage the loads on these blades. So this type of configuration pushes the limitation of today's technological and logistical infrastructure. And so the BAR team, within the BAR team, we're really focusing on the solutions of improving, number one, improving the multidisciplinary design analysis and optimization tool chain at NREL for large flexible blades. And this is the talk that Pietro is going to give. Also, we're interested in developing these controllers and capabilities for reducing the loads and managing the tip deflections for very large flexible blades. And this is a talk that Nakar is going to give. And finally, we've developed more accurate aerodynamic models for these very large flexible blades. And this is the talk that Kelsey is going to give. So with that, I will hand it over to Pietro.
Thank you, Nick. and welcome everybody to my talk. I will go through the design process that we have been conducting within the BAR project. And when we talk about design of wind turbines, necessarily we end up talking about multidisciplinary approaches. There are several disciplines that we have to consider: the aerodynamics, the structural design, the controls, the wind farm interactions, and so on. However, when we talk about large flexible rotors, these challenge existing low fidelity methods that have been traditionally being used for the design of wind turbines or for the exploration of the solution space, and require multi-fidelity approaches. So when we talk about design at NREL, historically we have been using WISDOM. And I will talk briefly about it. It's a multi-fidelity design approach and tool that is publicly available. However, it has we have been improving it quite a bit in the past 2 years, but it also has some structural, some limitation, inherent limitations, especially for the analysis of very flexible blades. We therefore come up with a new framework for the structural analysis of very flexible blades. It's called Sonata, and I will show you a little bit of details about it. For the ones of you who are into the world of structural analysis of composite structures, it uses VABS, but it also uses an alternative open source software. We have also implemented Roscoe, and Nikar later today will talk about it. It's the open source controller. And this because the control is more and more important with these very large rotors. We have also linked all these 3 pieces to OpenFast. That is the Aeroserve Elastic solver that is developed at NREL. And we have been using and improving BeamDyn, the geometrically exact beam model of OpenFast. Once all these 4 pieces of the cake were ready, we have been linking them to NUMAD, and that calls ANSYS. NUMAD is the 3-dimensional finite element tool for the blade structural design developed at Sandia National Labs. NUMAD uses ANSYS, the solver ANSYS, and from WISDOM we send them the blade model, and from OpenFast the loads. Sandia did their detailed design, and we iterated back to WISDOM, and we completed the design loop. Let's talk about WISDOM. Most of you have heard about it. WISDOM integrated design tool that has been developed at NREL for a number of years, approximately 10 now. It's based on the library OpenMDAO, which is developed by NASA. MDAO stands for Multidisciplinary Design Analysis and Optimization. If you're active in the world of optimization and you're not familiar with this library, you should take a look. It's very nice. It's very powerful. WISDOM is fully open source, and it's based on steady state models. And you see here a list of the models that we have been using within the BAR project. We have a Rotor model, drivetrain model, controls, tower, substructure, balance of stations, and cost of energy calculator. All these models are connected within a Python framework. And there is a documentation online, and there is also a tutorial that I held a few weeks ago with a rotor blade optimization example. There is a recording available, so please get in touch with me or Nick if you're interested, and we'll be happy to assist you. We said WISDOM is great, but it has some limitations. Especially it's low fidelity, and it's not powerful enough to analyze in details lender composite structures as we want to do in the BAR project. We therefore developed a novel framework called Sonata. It starts from a cooperation with the Helicopter Technology Institute of the Technical University of Munich in Germany and the Aerospace Department of Politecnico di Milano in Italy. It's again open source, an open source Python code built on the finite element library Phoenix. For the ones of you who are active in the world of finite element analysis, Phoenix is really powerful, and it can be used also for CFD calculations. Sonata integrates the solver VABS. That is the industry standard for cross-section analysis, and the novel solver AMBA4, which is an open source alternative, and we validated the tool chain against literature results. As a result, Sonata is a unique framework with unique capabilities. It's the first open source framework that generates the 6x6 stiffness and inertia matrices. And the next diagram shows what Sonata exactly does. We start from a three-dimensional blade design. We discretize 2D cross sections along blade span. Here you see 6. We usually use a finer discretization, for example, 30 stations. We mesh them two-dimensionally, and we pass the mesh to VABS or AMBA4, the cross-sectional solvers that give us fully populated 6x6 stiffness and inertia matrices that are then fed to a 1D beam finite element model. In our case, that's BeamDyn, the geometrically exact beam formulation of OpenFast. You see at the bottom a DOI. That's the link to a journal paper that was recently published that describes Sonata. And here you see some, in this slide, you see some animations of one of the bar designs walking across from blade root to blade tip. You see in the title, the section. The only difference between left and right is that on the left, we don't scale the axis, on the right, we do. And you can appreciate that Sonata is pretty detailed in terms of design, and we have all the different materials and all the different geometries accurately modeled. And it's a tool we are very proud of, and that we hope we can be used in the next years. Another module that we have implemented last year is a module that simulates the rail transport of the blades, and that allows control bending during curves. The constraints avoid derailment of the train and excessive strains induced to the structure. And we have been targeting the interior of the US and the main lines of other regions. That converts to the ability to navigate 13 degrees horizontal curves and 2 vertical curves with a radius of 2,000 feet. On the right, we see you see another animation. We are looking at a blade from the top with a bird's eye view of blades and tracks. The blue line represents the suction side, the red line represents the pressure side. And we see that up to 5 degrees of lateral curves, we don't need any bending. That's the first image. Then with increasing curves, the blade no longer has to be bent to successfully navigate the curves. And we are targeting 13 degrees. So we must be able to navigate a 13-degree curve. So this is another animation at the top. You see a 13-degree curve. The current limitation is 70 meters. That's the industry standard. And that's because up to 70 meters, we don't need to bend the blade. Beyond that, beyond 70 meters, we must. And you see here the clearance, and that is in green light. And when the blade is bent, we can satisfy the transport without exceeding any constraint. Vertical curves are not problematic, but in all this, flapwise blade stiffness must decrease to navigate 13 degrees curves. We have to go down to avoid excessive strains and derailment. As a result, 100-meter blades must be designed downwind. Not only the flapwise stiffness goes down and we move to a downwind configuration, we also have to play with the control strategy of these rotors. And so the downwind rotors are operating currently with a lower cutout wind speed set instead of the traditional 25 meter per second to 19 meter per second. And that's because downwind rotors at high wind speeds have the blades flapping very close to the tower. So lowering the cutout wind speed helps us operating with these very flexible blades. And we have also implemented a pitch to stall shutdown strategy. A standard shutdown strategy has a pitch to feather pitch maneuver. That means that the pitch is increased when the shutdown is active. In this case, we reverse the operation and we decrease pitch. We enter into stall, and this pushes the blades away from the tower and not flapping towards the tower. I should also mention that we are in a healthy competition with the low wind project that is running at DTU Wind Energy in Denmark in a cooperation with Vestas. I will go briefly over the bar designs. There is a paper coming out soon where all the details are explained and listed. We are bringing ahead 4 bar designs from 0 to 4. 3 are upwind, 2 are downwind. 3 of them are rail transportable, and 1 does not need to comply with any transportation constraint, and it's kind of the reference. And bar 3 is segmented. Note that the upwind rail transportable blade is shorter because we cannot make an upwind blade with a 100-meter blade length unless we go for very, very high cone and tilt angles. Also, appreciate the fact that the rail transportable blades are straight to be able to navigate left and right on the lateral curves. The downwind rotors have a lower cutout wind speed, and 3 designs have carbon fiber spark caps and 2 have glass fiber spark caps. In terms of the designs, again, here I'll be brief, but downwind designs reduce blade mass and cost. Heavy tow carbon fiber reduces blade mass at a slight increase of blade cost. And downwind designs have lower capital expenditures. In terms of annual energy production, however, downwind reduces AEP for the same rotor size. Now, let's remember that bar 4, that is the rail transportable upwind, has a smaller swept area and therefore generates less annual energy production than the downwind designs. And overall, downwind designs with carbon fiber spark caps is found generating the lowest levelized cost of energy. So conclusions of my talk. We have been developing and demonstrating integrated design approaches within the bar project. For a given rotor, upwind designs generate higher annual energy production than downwind configurations, but are seen suffering tighter logistical constraints. Thanks to control bending during rail transport, downwind designs support larger rotor size and lower levelized cost of energy. Downwind designs benefit from low cutout wind speed and a pitch to stall strategy for shutdown at and below rated wind speed. And heavy tow pultruded carbon fiber that is investigated at Sandia National Labs in the spark caps is a promising pathway to reduce LCOE. There is a lot of ongoing work. Here are at least some. Nick and I are working on the elastic stability of these rotors in OpenFast. We certainly need better airfoil polars at high Reynolds. This is a big gap in literature. We have been using X-foil, the Solver X-foil. In this project, we will shift to a 2-dimensional computational fluid dynamics framework developed that has been investigated and brought ahead at NREL. It would also be nice to validate the results. Downwind have historically suffered from issues related to low frequency noise and increased fatigue. We have some preliminary evidence that these issues might no longer apply for modern designs, but we don't have a final answer yet. And finally, we are investigating formal multi-fidelity design approaches within the WISE project that is funded by ARPA-E. Here I list some publications that are relevant. The top 2 are under submission, and they will appear in the Journal of Wind Energy Science in the coming weeks. And I thank you for your attention.
Okay, great. Thank you, Pietro. We'll move on to the talk from Nakar now.
Hi, everyone. Again, my name is Nakar. I'll be talking about the reference open source controller and how that applies for this BAR project and large flexible rotors. So to start us off, why do we need Rosco for BAR, and what was wrong with kind of the old controllers? For one, we're rapidly iterating through turbine designs in this project, so there's a lot of development happening within Wisdom and all these other tools that Pietro just discussed, and so for each iteration, we need a new controller. And so the legacy reference controllers that we use here at NREL required more complex and extensive tuning processes. So what we've done with Rosco is implement some automated tuning processes so that with a change in rotor design, we can quickly and easily get a new controller for it. Additionally, we were looking at some novel kind of control solutions. I'll talk more about these, but these come with tip speed ratio tracking, some peak shaving, and more kind of specific items for this project itself. Additionally, dynamic simulations are needed for large flexible rotor design. So why do we even need a controller to begin with? As we get into these larger, more flexible rotors, we need to run open fast simulations and dynamic simulations, and the results from these start to bring design constraints to light. And so of course we need a controller to do that works well. So kind of in a similar vein, this controller performance can significantly affect the rotor itself. And so if we have a poorly performing controller, we can't accurately assess how good a blade design is. This means that really the controller formulation is particularly important during these co-design processes, where co-design meaning that we're kind of at the same time in conjunction designing the controller with the rotor itself rather than just fixating on the rotor and then designing a controller for it. So kind of coming back to this design process workflow that Pietro had brought up, really I'm focusing here on the Rosco block, and this can really be broken down into 2 different aspects. First, we can kind of start with the Rosco toolbox, which is then the tuning process that we use for Rosco. So when Wisdom itself might change the rotor, might change the blade design slightly to more flexible blades, stiffer blades, what have you, then we can pass that to the Rosco toolbox, and within the toolbox, we can take this rotor design and basically write the input file to Rosco, which is the controller formulation. So the controller here, I'll talk very briefly about this. As Pietro mentioned, there is a tutorial for Wisdom. Similarly, there is a tutorial available for implementing these tools. But Rosco basically, the Rosco toolbox will then run through the tuning process for the controller, pass this to Rosco, and Rosco is the controller implementation, which then talks to OpenFast during a simulation. So the standard controller, I think many people might be familiar with this, but to give a high-level overview, we kind of have 2 different types of controllers that are generally implemented. There's a generator torque controller, which of course is modulating the generator torque to generally maximize the power. So below rated operation, the torque controller will be trying to maximize power, and then the blade pitch controller will kick in once we reach rated wind speeds, and that will regulate the rotor speed. And this can be done in a few different ways. So what did we change here? So in region 2, this below rated operation, we focus on the torque controller there. And some of the legacy methods can be subject to modeling errors and can reach their kind of constraints once we get into more highly flexible blades. So during the design process, these wind turbines are often designed for kind of an optimal aerodynamic efficiency at a specific tip speed ratio. So the ratio of the wind speed to the tip of the blade. And so instead of kind of following these more simple methods that were used previously, what we can do is design a controller to track this tip speed ratio and try to keep the rotor spinning at that speed. What this does mean is that we need a wind speed estimator to accurately understand what the wind speed is at the rotor plane in order to implement this. In region 3, This is almost always a gain scheduled controller. For gain scheduled here, what we're saying is that the sensitivities of the rotor itself to changes in wind speed are higher during, lower near rated operation, and then once we get further above rated, they're a bit higher. And so we've introduced some kind of more modern methods to model these sensitivities and tune our controllers based off of that. So the way that we're doing this is we're looking at the power coefficient tables, and we're using CC Blade, a steady-state BEM solver, to generate the power, thrust, and torque coefficient tables. Kelsey will later talk about some of the challenges here, but for control purposes in this initial work, we're pretty happy with the results from this. And what we could do then is look at what kind of a steady-state trajectory, and so we can kind of understand where the turbine will be operating along this surface and tune our controllers based off of the kind of coefficients that come from this analysis. So then we can determine the system parameters and the controller set points as we operate through below and above rated operation. And then additionally, we can use these tables in the wind speed estimators in Rosco to then accurately estimate the wind speed. So in addition to kind of some updates to these, that's kind of maybe two primary parts of the controller, there's some transition regions between below and above rated that kind of historically have come with some higher loads, and we've been able to smooth that out and reduce loads there. We've implemented the wind speed estimator. We've implemented a pitch saturation module, where the primary purpose of this is in near rated operation, we can kind of clip the rotor thrust and reduce tower loads. There's some shutdown procedures that Pietro mentioned earlier. We also have individual pitch control, yaw control, and floating offshore wind turbine control modules. And then finally, for this project, we implemented a specific distributed aerodynamic control process, which I'll talk about more now. But so first, before we go on, the Rosco is implemented in, it's available on GitHub through the Rosco toolbox linked here. And as I mentioned, there's also a tutorial on how to implement this. From a high level, how this is implemented is we start with some tuning parameters. Within Wisdom, we can just kind of automate this process of what these are. Otherwise, the user defines these. And really for the controller tuning, it's just a handful of parameters and then turbine parameters. These get passed to the Rosco toolbox, where, as I mentioned, we tune the controller. And then this gets passed on to the Rosco controller itself, where we can run some OpenFast simulations. And then finally, what this enables then is we can run some optimization. So from the OpenFast simulation, we can do some loads analysis and feedback kind of the results from that to Wisdom, or as Pietro mentioned, Weiss, and this kind of more formal approaches, and run some optimizations for the controller itself. So as I mentioned, I'll talk a little bit about distributed aerodynamic control. So why do we care about distributed aerodynamic control for the bar rotor? As it's been mentioned many times, it's really highly flexible blades, and they can, because of this, they can see large ultimate and fatigue loads. They also, because they're so big, can be limited by pitch actuator constraints, where the blades can't pitch very quickly. So one method of trying to reduce these is to introduce distributed aerodynamic control, where the idea is that we can change the aerodynamics more quickly through a small actuation region along the blade itself. There's this done kind of in numerous different ways in the literature, but we're focusing here on trailing edge flaps, and there's kind of a nice diagram here showing what that looks like. So from a controls perspective, we've worked through some formulations for an automatic controller tuning process similar to those for the rest of the controller. And what this comes out to be is we basically we give the controller tuning process what we want the blade root bending moment response to look like. So we say how quickly we want the blade root bending moment to be reduced when there's, say, a gust in wind. And so this is nice, and the controller tuning process will do this and basically produce the same load response for any flap position or size along the blade. So here we have on the left kind of a diagram showing an extreme operating gust, and for a 5, 15, and 25%, meaning 5% of the blade is covered by the flap, etc. We see that the 5% flap in the third down plot has to actuate a lot more than, say, the 25% flap, but we can achieve the same response. So this is great because we can kind of consistently tune controllers regardless of the flap, but then we might want to know what is the best response we can achieve. And so that's where kind of the wisdom and the optimization workflow comes in. And so on the right, we see that based off of these kind of two tuning parameters, there is a nice space that kind of comes with a nice minimum where we can reduce these blade root bending moments. And so now there's ongoing work with integrating this into wisdom and kind of doing some more complete co-design studies where not only do we optimize the blade flap controller, but then we can also say, now that we've been able to reduce these loads, maybe we can shave some weight from the blades and make them more flexible or something like that. So in conclusion, the Rosco controller itself implements kind of an industry standard wind turbine controller that has some of the more modern control features that we might want as we get into these larger, more flexible rotors. The Rosco toolbox then implements this automated controller tuning for this controller. So regardless of the rotor and changes that might come with it, we can automatically tune the controller and rapidly iterate through design iterations. Wisdom has been linked with Xfoil, where this is where we're able to determine the aerodynamic airfoil characteristics for these DAC devices. And finally, now we have this automated controller implementation where we can run through this entire design process in automated fashions without the need for a person to step in and tune controllers and things like that. Going forward, kind of one large thing that's happening is we're continued integration of Rosco into the optimization framework. Wisdom has kind of, since, as Pietro mentioned, we're formalizing it under the WISE project. So kind of working forward with that so we can enable full co-design optimization studies. Additionally, the way, I guess, the extent of our methods now and the tools now, we're not modeling the structural effects of the addition of trailing edge flaps and purely focus on the aerodynamic effects. So there's some hope in being able to better understand the structural effects of the blades from adding these devices. And then, of course, we're going to continue to develop these advanced control features and tuning processes within the Rosco tool chain to enable that. Thank you.
Great. Thank you, Nakar. So we'll now go into the aerodynamics talk from Kelsey.
Yeah, thanks, Nick. So there's been a lot of talk today about large turbines, large blades, the benefits of all that. But something that comes along with larger turbines is increased blade flexibility. And this increased blade flexibility can lead to the actual path that the blades travel, leaving this kind of nominal two-dimensional rotor plane. Also the near wake, which is the region right behind the turbine, this area can diverge from a uniform shape. There are increasing interactions between the blades and this near wake, and there's also increased unsteadiness and three-dimensionality of the aerodynamic effects. So those are all things that are caused by increased blade flexibility. Other challenges for modern turbines is that they have curved or swept blades. There's skewed flow from yaw inflow or turbine tilt. And also, if you have a floating offshore turbine, not only do you have large blade motion from the flexibility, but the whole rotor itself can experience some large motion. And so those three things can also lead to these effects of the larger flexible blades. So, for example, if you have an upwind turbine, the blades actually start with cone, they actually start more out of plane, and during operation, the blades actually bend back into more of a two-dimensional plane. And because there's a risk of tower strikes, the deflections of the blades are actually smaller. Versus if you have a downwind turbine, which has been talked about a lot today, especially for bar designs, the blades actually start more in a 2D planar configuration, and during operation, they bend more out of plane. And because you don't have to worry about tower strikes, you can have larger blade deflections. So, Nick. So, thank you. So what's the problem with all of this? So these things happen. So the problem is that The standard aerodynamic model that's used in wind turbine design uses this method called blade element momentum theory. This theory it started development in the 30s. It's very fast. It can take on one simulation will take just a few minutes to run typically, and it's reasonably accurate for simple inflow or operation conditions for kind of the more traditional turbines. But there are a lot of assumptions that go into this model. In particular, there are 2D, it assumes that there's a 2D steady axisymmetric inflow, that the rotor does not deviate from a two-dimensional rotor plane, and that there's no turbine near wake interactions. And so if you recall, I just said that flexible blades violate all of these assumptions. So many of the BEM assumptions are violated by these highly flexible turbine blades and floating turbines. So that necessitates a moderate fidelity code that's capable of modeling such complexities. So what are our options that we can use besides BEM? So you could use computational fluid dynamics or CFD methods. These are very accurate, complex codes that are able to capture these complex features. However, they have a very high computational cost. The higher fidelity ones, there's a range for CFD, but the higher fidelity ones can take on the order of hundreds of hours for a single simulation to run. So that limits the number of simulations you can perform, and that's an important consideration for loads analysis of turbine design. So another option is free vortex wake methods. These are moderate fidelity codes that model the wake directly. They have a lot fewer assumptions associated with them than BEM. They capture the prominent wake physics, and they have a moderate computational expense. So on the order of about 100 hours. So more than BEM, but less than CFD. So these free vortex wake methods are a moderate fidelity model that enables accurate simulations of highly flexible blades in challenging inflow conditions. So what exactly is a free vortex wake method? So they're essentially a way of concentrating the most important wake information into discrete points that are convected with the background flow. So there are a lot of different ways to do that. Free vortex wake methods are a pretty broad topic. You can model these points as either particles, lattice, or filament approaches. So in these pictures here on the left, it starts as a lattice or a mesh approach, and then you can see it turns into just a filament approach further downstream. And in the picture on the right, it starts again as a lattice method and then turns into just tracking these particles. So there's more to these methods than just tracking these points. There are also options for computing the circulation on the blades and how the wakes actually evolve or convect downstream. I'm not going to talk much about those options today. And some of these methods have already been coupled to structural solvers. So this is a really wide topic. And so what the big thing that we've done is integrated some of these methods with OpenFast. So this allows for the wakes of highly flexible turbines to be modeled along with the aerohydroservoelastic turbine response. So the full turbine response capabilities of OpenFast. So this is a schematic of kind of the basic modules of OpenFast for an individual wind turbine. And typically in this code, the aerodynamic loads are computed using this module called Aerodynamic, which uses just BEM, either with or without a lot of available corrections. And so what we've done is actually modified it so that the user can either still use BEM or use a free vortex wake code called OLAF. So the user now has an option between using BEM or OLAF, our free vortex wake code. So what exactly is OLAF, our free vortex wake code? So like I said, free vortex wake methods are essentially a way of concentrating the most important wake information into discrete points. And these discrete points are called Lagrangian markers. And essentially new Lagrangian markers are created at every time step and released from the turbine blades. If you're in the near wake or right behind the turbine blade, they're convected as a a lattice or basically a vorticity sheet from the turbine blade. And then at a certain point downstream, we say that this vorticity sheet instantaneously rolls up to be just a tip in a root vortex. And so that's when it becomes a filament approach. So you just have these Lagrangian markers connected by a single straight line. So that is on a basic level how our Olaf method works. And if you see here, this is an animation from the code. So you can see the turbine spinning. There's this sheet of points that are convected away from the turbine blades. And then at some point, it might be hard to see depending on the screen, but at some point this sheet rolls up and you just see lines coming off of the tip and the root of these sheets. So from a fundamental level, that's how our Olaf method works. We've done a comparison between Olaf, BEM, and SOFA, which is a CFD code used a lot here at NREL. So we did comparisons for the bar 2 downwind turbine for just uniform 8 meter per second flow. So this is a very simple case. We actually did not use a controller. So in all these simulations, the rotor speed and the blade pitch of all the turbines are specified, so they're the same. And these are for 600-second simulations. And so showing here each plot, these are the time averaged means. So we have rotor power, rotor thrust, out of plane blade root bending moment, and side to side tower base bending moment. The blue line is for BEM, the green line is for Olaf, and the pink line is for SOFA. And so we're kind of using SOFA as our truth solution. I'm using quotation marks. Since it's such a high fidelity code, it's typical when you're doing verification studies like this to use CFD as your truth solution. So what you can see from all these plots is that the Olaf results, the x-axis is varying yaw misalignment of the turbine. So you can see that the Olaf results match the SOFA results very well. BEM captures the trends, but the actual values are off. And if you look at the actual percent differences of these results, if Nick could click, please. No, okay, well, moving on. So I have plots of the actual percent differences, and you can see that the average percent differences for the Olaf results are around, actually in this plot in the upper right-hand corner, there we go. On the right here is the average percent difference for all the loads we looked at. The average percent difference compared to SOFA for BEM was, I think, around 13.5%. And for Olaf, it was about 1.5% difference for all these loads. And if you look at the computational time in terms of CPU hours, BEM cases took about 10 minutes to run. The Olaf simulations took about 144 CPU hours to run, and the SOFA simulations took around 260 CPU hours to run. So when you have parallelized codes, it doesn't in real life take that long, but so CPU hours, that's how long it took. So essentially, Olaf shows really strong agreement with the mean SOFA results and took nearly half the computational cost of SOFA. And again, BEM captures the trends, but the actual values are off. So we did the same thing. So those are time average means. We did the same thing for the standard deviations. I won't spend a lot of time on these plots, but basically this is the same rotor power, rotor thrust, bending moment, and tower base moment. And again, you can see that the Olaf results very strongly agree with the standard deviations of the SOFA results. And again, BEM mostly captures the trends, but the actual values are off. So we're showing that not only is Olaf really good at capturing the time averaged mean values of a higher fidelity CFD code, it also captures the standard deviations really well. And that's very important for the design process. So lastly, just some conclusions and ongoing work. So the initial development of Olaf is complete. This code, it's an open source code. It's available in the OpenFast Git repo. I have the link there if anyone's interested. And we've also published a Olaf user's guide and theory manual. This is available as a technical report, but it's also online with all the other OpenFast documentation. So in our initial comparisons, we've shown that for steady, really simple inflow comparisons, we've got really strong agreement between Olaf and SOFA, whereas BEM is lacking. So our ongoing work is obviously further validation of this code. We're going to do some validation work with the Summer D turbine for comparison of a wide range of experimental data from a two-bladed, highly flexible downwind turbine. This OLAF code is also going to be used within BAR to fine-tune some of the turbine designs and some other applications. And we're also continuing OLAF development under the ARPA-E WISE project. There is also a training that we did with OLAF a few weeks ago that's available online if anyone's interested. But this code is still in development and just going to get better. So thank you.
Okay, thank you very much, Kelsey. Yeah, just one final slide to kind of wrap up, and then we'll take questions. But yeah, just in general, I think we've walked you through today some of the challenges that we face with these very large onshore blades. The first being the challenge of transportation, right? So we came up with an alternative solution to the jointed blade, which is the rail transportable blades. There's these challenge of designing the flexible blade, so using wisdom, the control strategies, looking at stability analysis are the solutions that we've developed. And then obviously, as Kelsey just talked about, challenges of modeling the correct aerodynamics of these very flexible blades when you have these out of plane rotor deflections, and these old models are no longer valid. And the solution here is obviously developing OLAF, the mid-fidelity free vortex wake code. That is coupled to OpenFast. So with that, I think we're right on time to be able to answer some questions. I'm going to actually have to exit presentation mode so that I can get into the questions. So I will do that. I'll ask the panel to turn their cameras back on. And please, if you have any questions, type them into the chat. But I think we have one here for Pietro. So this is from from Mike Robinson. And the question is, Pietro, why do you believe that modern two-bladed downwind designs will not be subject to the infrasonic tower shadow pulse?
This is a good question, Mike. So one clarification, we have been looking at three-bladed designs, not two-bladed. But aside from this, there are several. So Hitachi, the Japanese conglomerate, has been manufacturing downwind three-bladed turbines, and they don't report excessive noise or excessive fatigue. And also, like the people who observe the turbines have not felt any noise. There has been projects at DTU led by Frank Bertagnolio. And he looked at the infrasound noise of some downwind turbines at RISO, the research lab in Denmark, and he also hasn't seen any special noise radiation in the low frequency. And one reason behind this difference is that the turbines in the 80s were very different. The tower was very bulky. The rotor was very close to the tower. Now modern turbines, they have a completely different size, right? So the tower is much more slender. The blades flap much farther away from the tower. And it's certainly something to validate, but so far, it might be just a very bad scar on the industry shoulders, and we might be away from it.
Okay. Thank you, Pietro. Maybe one other question for you here. We had the question, can you explain the term increasing fidelity?
Yeah, so all these talks that we had, we have been talking about fidelity. In Kelsey's example, it's maybe easier to understand. She has the BAM model, which has several assumptions, and she has been developing this novel framework, which removes some of the assumptions. The same holds for wisdom. For example, wisdom is based on, first on steady state models, and we have been moving more and more into time domain simulations. And second, for example, pre-comp. Pre-comp is a cross-sectional analysis solver, which neglects several terms. For example, the shear stiffness terms. The pre-comp does not compute shear stiffness terms, but those are important terms. And so we had to move to higher fidelity solvers like AMBA4 or VABS, which predict these terms.
Okay, thank you, Pietro. This to me is a two-part question, so I'm going to ask it to both Nakar and to Kelsey. Historically, one of the major concerns with very flexible downwind designs were the potential of unloaded snapback from the spring loading when the rotor is suddenly unloaded. How can this be handled? So Nakar, maybe you can talk a little bit about the control side, and then Kelsey, maybe you can talk about some of the wakes or aerodynamic impacts of the blade kind of snapping back and forth.
Yeah, so I think that might have been part of the motivation for exploring the distributed aerodynamic control devices a bit more, is that they do have kind of higher response times, and it makes it so we can change aerodynamics to help prevent that. I'd say specifically at some point the controls maybe can't entirely alleviate that issue, and that's where then the kind of the back and forth between the controls and the rotor design itself comes to play. I know Pietro also saw some of this and mentioned it briefly with his shutdown strategies during certain design load cases. By changing the direction in which we pitch the blades during shutdown, we can help prevent tower strikes that way.
Okay. Can you say just a little bit more about that last one, Nakar, in terms of maybe, you know, the aerodynamic force is still keeping, is that how it is? The aerodynamic force is still keeping the tower or the blade away from the tower if you pitch to feather?
That I might deflect that to Pietro. I think he explored that a bit more and might be able to speak more to that than me.
Yeah, so these are it's a good question. In a shutdown strategy, both for upwind and downwind blades, if the shutdown is a very rapid maneuver, the blade acts as a spring, as the question said, and flaps the other way. In upwind, that means that the blade flaps into the wind, so it deflects away from the tower. In downwind, that the trend is the same, and so we flap towards the tower, and that's a dangerous behavior. So the way we solve this, or we address this, is to change the pitch maneuver at and below rated wind speed. This increases the thrust instead of decreasing suddenly lift and drag. And by increasing the drag, the flap suddenly flaps in the other direction, so not towards the tower, but away from the tower. And we can do this game. Numerically, it works very nice. We need to validate this in the field and see how it behaves. We can do this game at and below rated wind speed, because above rated wind speed, it doesn't work, because we would need to cross. If you have in mind the airfoil polars, we would need to cross a region where lift grows, and so the loads would be excessive. But again, below and rated wind speed, numerically, it works very nicely.
Thank you, Pietro. Yeah, Kelsey, maybe you can talk a little bit about what Olaf might be able to model that the BEM code couldn't in this type of example.
So we haven't specifically looked at this yet, but this is definitely a case where I would say you could not use BEM and expect to get good results. Not only are you having really large and sudden blade deflections, but especially if the blade is moving back and forth rapidly, you're going to have really strong interactions between the blade and the near wake, and really strong tip vortices, which BEM can't really handle any of those situations. So I think that would be a really good example of a place where you would absolutely need a free vortex wake method to handle those situations.
Yep. Okay. Yeah. Thank you all for that one. We had a question in the chat. Do larger wind turbine rotors produce more noise? Nicole kindly answered that one to say if you increase the tip speed, yes. If you increase the rotor size, lower the rated rotor speed, right? And keep the tip speed constant, it'll roughly stay the same. So yeah, I think that's nothing else really to add to that one from my end. I don't know, Pietro, if you have any more thoughts on that.
No, we can just add that within the BAR project, we have also developed an acoustics module, which is now part of OpenFast. You find it all in the OpenFast master branch. but yeah, Nicole is absolutely right. Noise depends mostly on the tip speed, blade tip speed. So as long as we keep that tip speed constant, noise is not increased a lot.
Great. Okay. Thank you for that. We have a question from Matt. Thanks for the great presentation. Will there be different manufacturing requirements for larger, more flexible blades? And will the existing U.S. supply chain be able to accommodate these requirements and build the new bar blades? Pietro, do you want to take a crack at that one?
Yeah, so the blades are big, but they're not that weird if you think about the offshore blades. Offshore blades are bigger than that. They are bigger than standard land-based wind turbines. And so we don't expect any major problem, and especially with the fact that they can be rail transportable. This opens up and the possibility to manufacture them within the U.S. and then transport them to the site with the train. On the manufacturing side, an important aspect is that these downwind flexible blades are straight, and so they actually simplify somewhat the manufacturing process. The pre-bend is a complicated aspect to deal with during manufacturing because the molds have to be curved, and you have to close two molds that are two bananas. So straight blades simplify the manufacturing process somewhat.
Okay. Any other questions? Okay, Alex, thank you. We'll have the recording up soon. Okay, great. Well, I think we can wrap up there, and maybe I'll ask a question to the audience, and maybe this is unconventional, and I'm going to break the fourth wall here, but I'll ask you all how big you think onshore wind turbine blades can be. And like Daniel said at the beginning, I think throughout history, people have had guesses of what that is and kind of very firm ideas, but we keep getting bigger and bigger and bigger. So my question, I guess, is more of a challenge to stay open-minded and continue to push the envelope and reach new frontiers in blade length, because it does have a big impact on the levelized cost of energy. And I think we can continue to make big impacts and strides in these areas. So with that, I would like to thank our panel, Pietro, Nakar, and Kelsey. Thank you very much. And thank you to the audience for attending and paying attention and asking great questions. So thank you all and have a great day.
Thank you, Nick.
Thank you, everyone.
Thanks, Nick. Thanks, everyone.
Thank you. Bye-bye.